Okay, the next speaker will be Victor Vargas from Mexico. He will speak about dynamics of pollinator, plant, and herbivore populations. Let's go, Victor.
Okay, thank you very much to organizer for giving me the opportunity to talk with you about of dynamics of pollinator, plant, and herbivore population. This work is joined with Faustino Sánchez Garduño from Facultad de Ciencias of UNAM and Miguel Ángel de la Rosa Castillo, professor at the Universidad Juárez Autónoma de Tabasco and Cátedra CONACYT. Okay, then it's okay. Then the context of the problem is the next. What you see in this case, the plants has many problems to grow and depend on many factors as shown in the figure. Oh, sorry, I will be turn off my camera because maybe we have problem with the internet. Therefore, optimize, I will be turned off, okay? Okay. Then I say that the growth plan depends on many factors as shown in the figure. For example, we have an herbivore and we have a pollinator and another problem in the ecosystem. Observe that the relation between the pollinator and the herbivore occur indirectly through the plants, okay? Then, and that the reproduction of the plant depends on the pollinator, but not the reproduction of the pollinator. The plants grow and reproduction are highly affected by herbivores and this in turn require plants to survive. To write a mathematical model that describes this scenario, it is necessary to establish certain premises and then let's go to do this, okay? So, from the mathematical modeling point of view, to provide the sufficient condition under which the interacting population coexists is an important problem. Effectively, we like to conserve the ecosystem and then it is important to coexistence of population. In fact, there exists several dynamical behavior consistent with the notion of ecological existence, coexistence. For instance, when the mathematical model is an autonomous ordinary differential equation system, the coexistence could occur by means of the existence of a positive global attractor or by means of the existence of an attractive limit cycle, all of them in the positive octane of the phase space. Each one of these dynamical systems, this dynamical behavior that reflects different ecological situations. The role played by a third population which interact, for instance, as a predator, with other two which already maintain a mutualistic interaction, originates important problems from both an ecological and mathematical point of view. The specific types of interaction we are interested in studying are two mutualistic, which take the form of pollinator and plants. A third population, the herbivores, interact with the plants by consuming them, which from demographical point of view can be seen as predator-prey model interaction. The consumption of plant behalves the herbivores indirectly damage the pollinator population. This happens because such a consumption diminishes the opportunities of visiting plants behalves the pollinators. The specific type of pollinator plant and plant herbivores interaction can be described by different density-dependent functions. All of them reflect important ecological situations. In this work, we propose a mathematical model derived under the following feasibility assumption. It's clear that the fix a model is necessary some premises. One, if there are no plants, the pollinator population grows logistically. This means the plants are not vital for the pollinators because the plant can go to the other plants. If there are no pollinators, the plant's population decreases exponentially. The meaning of this is the existence of the pollinator is vital for the plants. The interaction between plants and pollinators are of mutualistic type. This means both of them obtain benefits from the interaction. The plants are pollinated exclusively by this pollinator, and the pollinator get nectar and pollen from the plants. The analytical form by means we measure such an interaction is by a functional response of type 4. The another premise is if there are no plants, the herbivores population decreases exponentially. The plants are the unique food source for the herbivores. And the last premise is the interaction between the plants and herbivores is of predator-prey type, taking the analytical form of a whole functional response of type 4. The whole functional responses of type 4 are of this form. The concept of functional and numerical responses originally were introduced by the American ecologist Hollin in the context of predator-prey interaction. In this, in his original paper, Hollin introduced the so-called functional responses of type 1, 2, and 3. The functional response of type 4 was introduced by the British scientist Haldane in the context of enzymology. Then the problem here is based considering the whole functional response type 4. The form of this function are as shown in the picture. The mathematical model that we describe is the next. We denote by xy, xt, yt, and zt the pollinator, plant, and herbivore population density and time t respectively. The following mathematical model capture the above assumption. Here, the growth of the pollinator depend of this equation, no? And the growth of the plant depend of this form of the, and the pollinator depend in this equation, okay? Here, the function f is a functional response type 4. G is a function that will be described in the next slide. X is a logistic growth. Also, Fy appear here, and this is the numerical response to the Holding functional response. Hy is also a Holding functional response of type 4. And the herbivore has one relation with the plant, draw this functional response. In this problem, obviously, all the involved parameters are positive, and the function f and h are functional response. By imposing condition on the function g is set that g in 0 is equal to 1, and the derivative of g at z is less than 0 for all z greater than 0, such function has the following ecological interpretation. Is the reduction rate of visit of pollinator to plant due to the plant's consumption behalf the herbivores. So, because the ecological interpretation of the variables, the region of interest in the three-dimensional space is a positive octane. No? Okay. The main contribution of this work consists in showing that the coexistence of the three populations forming the pollinator plant herbivore interaction model take place by means of a supercritical Hopf bifurcation. This task becomes hard if no numerical fixed assignment for the involved parameter is done. Moreover, in our mathematical model, two general functional responses of Holding type 4 are considered. As you see in the model, there are many parameters. And then to do calculus is very difficult. Okay. So then we do the analysis of our mathematical model. First, we find conditions to guarantee the existence of two equilibrium points in the positive octane. And second, we prove the existence of stable limit cycle. Why we are interested in these two concepts? Because we like to find the condition for the coexistence of the species, of the population, okay? Okay, the step to do this one are the next. First, we write the mathematical model as a polynomial ordinary differential equation system only for do one change of coordinates. Next, find the equilibrium point of the model is not an easy task. Then we process as follows. If I solve the system for the variables x, y, and z directly is very difficult, and maybe I can to do directly. Then we do the next. First, okay, identify which parameter or variables appear as a linear function in the system and then solve for this parameter or variables. Next, we find condition on the parameter to guarantee that the linear approximation has a pair of pure imaginary complex eigenvalues. Here, in this at this step, we identify a bifurcation parameters. Next, we apply the Kuznetsov formula to compute the first Lyapunov coefficient, L1, and also we need to prove or verify the transversality condition. Then this step are necessary to prove the existence of the limit cycles. And we have many parameters, then we can do many assignation to obtain this condition. Okay, in this proposition, we resume all the calculus that we need to do to guarantee the existence of an equilibrium point in the positive octant. The proposition says, whenever the parameter of the differential system satisfy this condition, at here we fix many parameters. Observe that all parameters are positive, where here Z0 is any positive real number. Then such system has two families of equilibrium point depending on the parameter gamma. This point has the form of this, and you observe that in the second coordinate, the point P0 has C, and the point P1 in the second coordinate has 2C. And then there are, in this sense, one relation between these two equilibrium points. Now, if gamma 0 take this value, then the Jacobian matrix of the linear approximation of the system at the point P0 with the value of gamma equal to gamma 0 has eigenvalues next. One of eigenvalues is real and negative, and also has a pair of eigenvalues imaginary. And also the equilibrium point P1 is locally unstable. Then this proposition gives us the scenario to apply Hopf bifurcation. Okay, the proof of this proposition is as follows. The point P0, X0, Y0, Z0 in the positive octant is an equilibrium point if and only if it satisfies the following algebraic system. E1 equal to 0, E2 equal to 0, E3 equal to 0, where EI once all the calculation carry out are. And then the expression for E1, E2, and E3 is here. And then here is where we need to look which parameters appear as a linear function or not. For example, here the variable x appear in the equation G2 and is linear, okay? But the another variables y and z appear but of degree 2. Then if I like to solve this system directly for x, y, and z, maybe it's impossible. But we have many parameters. Then we identify some parameters that appear here as a linear combination. And if you see in this three equation, all the parameters appear as a linear of degree 1. Then maybe we have many options to solve this equation. Then we solve the system in terms of the parameter k, y0, and m2, and then we obtain that k2 is this value, x0 depend of the another variables y0 and z0, and this is the relation. And M2 is equal to delta by this factor. Here, the factor R1 has this expression, and if you see the factor at this parenthesis, when we have R2, then we can solve R2 equal to 0, and then we obtain an expression for R1 more easy to use, okay? Then we do this one. Then we solving R2 equal to 0 with respect to parameter K, we have that K is equal to this one. No? With the above parameter assignment, what we obtain is the differential system has an equilibrium point given by this one, P0 is equal to this one, where X0 depend of Y0 and Z0. And is given as above, and Y0 and Z0 remain almost free, just satisfying the positiveness condition. At this moment, we find relation in the parameters to obtain one equilibrium point. And you observe that Y0 and Z0, you can to put any number. No? So the next step in the proof is compute the linear approximation at the equilibrium point and establish conditions so that we have a pair of pure imaginary eigenvalues. So by the other hand, if we choose phi equal to 2c, then the equation G3 becomes this form. And then we solve this equation and we obtain two roots. One root is y1 equal to c and y2 equal to 2c. If we use the root y1, we obtain only one equilibrium point. And for the root y2, we obtain another equilibrium point that has this form. The characteristic polynomial of the linear approximation has only one change of sign. Then it has a one positive real root. Then the equilibrium point is unstable. Then with this, we conclude the proof. And then we have two equilibrium points in the positive octant. And in the equilibrium point P0, we have that the condition of the relation of the parameter gives that the equilibrium point has one real negative eigenvalues and a pair of pure imaginary complex eigenvalues. Okay, so the next is then to prove the existence of an equilibrium point using the Kuznetsov formula. The theorem then is the next. Under the hypothesis of proposition 1, the differential system has only two positive equilibria that are P0 and P1. There is a supercritical Hopf bifurcation at P0 with respect to the parameter gamma with bifurcation value gamma 0, that take this value. And the equilibrium point P1 is locally unstable. The instability of the point P1 is already proved in the proposition. And the first part of the, to apply the Kuznetsov formula is also proved in the last proposition. So the emergences of the Hopf bifurcation at P0, it follows from the previous calculation and analysis. The remaining detail for completing the proof are: 1, to decide the stability of the emerging limit cycle, and 2, the transversality condition. For the item 1, we are going to compute the first Lyapunov coefficient by using the Kuznetsov formula. The Kuznetsov formula is the next. I recall briefly the Kuznetsov formula. When a differential system x point equal to fx mu in Rn has an equilibrium point P having eigenvalues plus minus omega I, it is a candidate to exhibit a Hopf bifurcation.
Ajá. Dime si te puedo ayudar con otra cosa.
Sorry. Maybe I don't know what happened here. Okay. Okay. And then if we have an equilibrium point with eigenvalues plus minus omega I, then we have a candidate to exhibit a Hopf bifurcation. In order to show that this bifurcation takes place, it is necessary to compute the first Lyapunov coefficient, L1, at the equilibrium point P of the differential system at the equilibrium P. When L1, when the first Lyapunov coefficient is negative, the point P is a weak focus of the differential system restricted to the central surface of P, associated to the pair of complex eigenvalues which cross the imaginary axis, and the limit cycle that emerges from P is stable. For this occur, we need that the eigenvalue cross the imaginary axis, is that we need to prove that the derivative of the real part of the eigenvalues is not zero. When L1 of P is greater than 0, the point P is also a weak focus of the differential system restricted to the central surfaces of P, but the limit cycle that born from P is unstable. Okay, and then the Kuznetsov formula that is very interesting and is a tool very important to do the to describe a Hopf bifurcation is the next. Let x point equal to fx, a differential system, having P0 as an equilibrium point. Consider the third order Taylor approximation of f around the point P0 given by this one. Assume that A, that is the linear part, has a pair of pure imaginary eigenvalues, plus minus omega I. Let Q be an eigenvector of A corresponding to the eigenvalue of omega I. Normalize it so that Q dot Q bar or equal to 1, where Q bar here is the conjugate vector of Q. And let P the adjoint vector so that the transpose of A applied to the point P is equal to minus omega IP, and P bar dot Q is equal to 1. If I denote the identity matrix, then the first Lyapunov constant or first Lyapunov coefficient, L1 of P0 of the system x point equal to fx at the equilibrium point P0 is 1 over 2 omega multiplied by the real part of these numbers. This number is a complex number, and then we need only the real part. And this real part divided by 2 omega is the first Lyapunov coefficient. Then, in our problem, then we need compute this number, and also maybe it's possible that the first Lyapunov coefficient with some relation of the parameter is equal to 0, and then I can to prove the existence of the limit cycle. But if we find a relation of parameter adequately, then maybe we can to find the first Lyapunov coefficient is not 0. Okay. To prove the transversality condition, you use the next lemma. This lemma is proved in some other papers. Let MB in beta be a parameter dependent real n plus n matrix, which has a simple pair of complex eigenvalues, sit beta plus minus or I omega of beta, so that sit at the beta 0 is equal to 0, and omega of beta 0 is equal to omega 0 that is greater than 0. Then the derivative of the real part of the complex eigenvalues is given by these numbers. Is the real part of this complex numbers, where here P and Q are in Cn, are the eigenvectors satisfying that M beta 0 by Q is equal to I omega 0 by Q, and transpose of M of beta 0 by P is equal to minus I omega 0 by P, where the following normalization condition is necessary to satisfy that that the transpose of the P bar dot Q is equal to 1, and the transpose of the Q bar dot Q is equal to 1 are required. Okay. Okay, then we need to compute the first Lyapunov coefficient. Okay. First, we carry out the linear change of variables for move the equilibrium point P0 to the origin. Now, we denote by A gamma the linear approximation at the origin. We denote by lambda 2, 3 of gamma the eigenvalues, so that we have that at the gamma 0 value, the eigenvalues are pure imaginary, as in the proposition. For lemma, we have that the derivative of the real part of the eigenvalues lambda 2, 3 that depend of gamma, then the derivative respect to the gamma of the real part evaluated at the gamma 0, that is the value of bifurcation, is this number, and this one is negative and is distinct of 0. Then we have that the transversality condition is held. So main way from the Kuznetsov formula, we have that the first Lyapunov coefficient is this one, where T is this number that is very big, and T2 is also one big number. But this number, T and T1 and T2 are positive. And then the first Lyapunov coefficient is negative, implying that we have a supercritical Hopf bifurcation. And then with this one, we conclude the proof of the theorem. To compute this number is very, very difficult. And then to compute, you use mathematical software to do operations and compute this number. But it's not easy because there are many parameters, and if you observe this Lyapunov coefficient depend now of the parameter K1, alpha 1, C, delta, C0, K, okay, and only this one parameter, because in after we fix another parameters. Okay, then now we show you numerical simulations to this problem. All the massive calculus and numerical examples were done with mathematical software, as say that. Okay, in order to obtain our numerical simulation, we choose the parameter values in such a way all of them satisfy our analytical result. In particular, because of the condition appearing in the theorem 1, we have that the vector fields which define the system 1 only depend on the three parameters C, K1, C0, alpha 1, gamma, and delta, where gamma is the Hopf bifurcation parameter with bifurcation value gamma 0 equal to this. So by choosing C equal to K1 equal to C0 equal to alpha 1 equal to delta equal to 1, we have that the equilibrium point of the system 1 belonging in the set omega, that is the positive octant, are the next. P0 is this number, and P1 is this number. Okay. Also, we know that the P1 is a unstable point, and the point P0 is a stable. Okay. Our goal is to illustrate the following three local dynamical behaviors. First, the asymptotic stability of the equilibrium point P0 for a bifurcation parameter value a little bit bigger than gamma 0. The next is the dynamic of the equilibrium point P0 for the bifurcation parameter value equal to gamma 0. And the third is the existence of the attracting limit circle bifurcated from P0 for a bifurcation parameter value a little bit smaller than gamma 0. Okay, we are going to carry out the simulation for each item separately. First, for item 1, by setting gamma equal to gamma 0 plus 1 over 100 and keeping the previous parameter assignment, the equilibrium point of the system 1 in the positive octant becomes P0 equal to this number. And P1 is this point. The numerical values at P0 are this one. You observe that we have a real eigenvalue that is negative, and we have a pair of complex eigenvalues with real part negative. Then we have an hyperbolic equilibrium point, and it is asymptotically stable. Okay, this is the first dynamics. So the next, for the item 2, by setting gamma equal to gamma 0, the equilibrium point of the system 1 in the positive octant becomes P0 equal to this one, and P1 equal to this one. So the numeric eigenvalues at P0 are a real, negative real eigenvalue and a pair of pure imaginary eigenvalues. Then the linear approximation is a center, and if we do the simulation, also we observe that the trajectory go to the one close orbit in the center hyperzone. Then here, 3 orbits with initial condition at Q0, Q1, and Q2, tending to its corresponding closed trajectory, and suggesting that P0 is a center in the 3-dimensional phase space. Evidently, is necessary to prove this one, but because here is only a numerical simulation. Okay, finally, for the item 3, we assign gamma equal to gamma 0 minus 1 over 10 to 5, and keeping another parameter value as those in item 1. In this case, the eigenvalue of the linear approximation are this one. Also, we have a negative real eigenvalue, and we have a pair of complex eigenvalues, and this point is P0 is evidently unstable, locally unstable, and the limit cycle appears here. The trajectory starting at the initial condition Q1, corresponding to the parameter value gamma equal to gamma 0 minus 1 over 10 to 5, and note that the attracting factor of the limit cycle, which is predicted by our result. Then to find the limit cycle is around of the parameter bifurcation. Then by this one, we use value of the parameter gamma near of the parameter bifurcation. Okay. This figure show a sort of summary of the dynamics of the system 1 depending on the parameter value gamma. You observe that in the parameter value gamma 0, that is the bifurcation parameter value, bifurcation value, then we have a center at the left to this number. We have a limit cycle, attracting limit cycle, and for gamma greater than gamma 0, we have an equilibrium point that is locally stable. In both cases, we have the coexistence of the population, the pollinator, plant, and herbivore. Okay, discussion and conclusion. In the following items, as a way of conclusion and discussion, we are listing in a few points that what we consider are of relevant contribution and some open problem we consider is worth of investigating as a natural continuation of our investigation. First, the introduction, what we call it satiety, which it is measured by a variant of the functional response of type 4, could result an interesting ecological mechanism. If you recall, the functional response type 4 has an maximum. With we have one function of this form, then the maximum represents the satiety of the population. Now, second, we are able to providing the sufficient condition on the parameter value for the emergence of an attracting limit circle for all proposed three-dimensional autonomous nonlinear ordinary differential equation system. Its existence implies the coexistence of the three interacting populations by means of an isolated periodical behavior. Indeed, this is a modest contribution in the effort of understanding the complex dynamics associated with three-dimensional nonlinear autonomous ordinary differential equation. According with our analysis, there exists a set of parameter values so that the system has a positive non-hyperbolic equilibrium point. Our numerical simulations show that the center feature is shared by both the linear system at the equilibrium point and the nonlinear system as well. Four, the description of those factors influencing the change in the abundance of the interacting population and the spatial distribution of them are two of the most important problems in population ecology. Because of this, we consider the incorporation of the spatial component in our studied model as an interesting problem. In particular, to carry out the analysis with the aim of searching the eventual emergence of ordered spatial distribution within the habitat where the population interact. Some aspects of this problem are under current work by some folks. Effectively, the spatial distribution is important because here now we have a partial differential equation, and it is effectively important because maybe if the pollinator like go to one plant, but maybe the winds move the trajectory of the pollinator, and then the pollinator come to another plant. Then in this sense, we need to consider the spatial distribution, okay? Thank you very much for your attention.